Hello, everyone. So today we're going to be bringing our conversation of entropies up to talking about reactions. So one of the important things to remember when talking about entropies of reaction is that almost all reactions and even the changes of state that we saw earlier are all going to have an associated entropy change with it. Because the entire point of a chemical reaction is I'm taking matter and I'm rearranging it. Well, this means that I'm going to essentially change the possible configurations of my chemical system. And as soon as we change the possible configurations, we change the entropy because can never forget about that available microstates factor. And so from here, we can essentially take advantage of the fact that we defined entropy such to be a state function. So since it's a state function, I can determine the entropy of any chemical reaction simply by knowing the entropy of my products and the entropy of my reactants and then taking the difference. However, again, make sure that you make note of the stoichiometric coefficients because again, the entropy of reactions that we're typically making use of are molar entropies. So if I have, say, the entropy per 1 mole of a substance, I have to take into account I may have 2 moles of the substance per single mole of reaction. So again, don't forget about your coefficients. This is often essentially shortened in notation to simply that the entropy of reaction is given as the sum of the molar entropies of the substances times their coefficients, where these coefficients can be positive or negative. However, one of the things that you need to take a special note of when calculating entropies of reaction is the fact that, well, there's often several common reference methods of giving entropy values. The most common is what's called our third law entropies. So these are essentially the absolute entropy of the substance, including its base entropy at 0 Kelvin. However, there's also another very common entropy term that you say may find in certain reference texts, which is called the entropies of formation. So these are essentially the analogs of our enthalpies of formation, where this is going to be the entropy to form 1 mole of product at from its elements in their most stable state. So again, we can examine the differences in between the entropies of formation and the third law entropies by looking at kind of a simple reaction. So we can do, say, the formation of methane from, say, coal or graphite and hydrogen. So this is actually one fairly common method of producing methane gas by essentially running H2 over a carbon source. So we can go ahead and calculate these from our third law entropies simply by taking the entropy of our methane minus the entropy of our carbon minus twice the molar entropy of our hydrogen. And so when we go ahead and put this all together, we get an entropy of reaction of negative 80.85. So again, not too surprisingly, as I go from 1 solid and 2 gas molecules to 1 gas molecule, I see a significant loss of entropy for this reaction, meaning that for this reaction to become favored, I have to have the reaction has to be very exothermic. In other words, it has to highly disorder its surroundings. Conversely, we can also calculate this from the entropies of formation. So again, because carbon is its most solid state carbon is its most stable elemental form, and the same thing with hydrogen, these have entropies of formation of 0, giving our entropy of formation of methane as 80.85. So again, these two methods do agree, and you can make use of either method. But where you have to really make sure to watch out for is that you don't mix and match. For example, if you find the entropy of formation for methane in one source, but the molar entropies of hydrogen and carbon in another source, you can get yourself into some real serious trouble. So make sure that no matter where you grab your entropies in the literature, that they're all of either third law or all of formation. So again, watch out for the potential mixing and matching of thermodynamic data when using multiple resources. However, one of the other things we have to acknowledge is that, well, most of our entropy values that we look up in tables are given at standard state conditions. So 298. Unfortunately, a lot of the reactions we care about aren't always run at 298 degrees. So we need to be able to account for any potential corrections due to temperature. And so we can essentially do this in a very similar way that we corrected for our enthalpy values by essentially just using a thermodynamic cycle and the feature of state properties. So for example, let's say I want to examine the entropy of reaction going from reactants to products at some temperature 2. So I'm looking for entropy of reaction at temperature 2. What I have is some reference entropy of reaction at temperature 1, because I can go ahead and look this up in a table. I can also, if I look up and go to a table, look up the heat capacities of my reactants and my products. So again, I can then correct for the entropies of my reactants going from T1 to T2, and the same thing for my products. And then in order to essentially figure out my entropy reaction by knowing these other three processes, I can essentially add them up. So I need to inverse this first step because I'm going from reactants at T2 to T1, and then the entropy of reaction at my old temperature, and then essentially heating my products back up. So again, cooling, reaction, heating is going to be the same thing as the reaction at my temperature of interest. Now, let's be honest, this is a little bit messy, so let's go ahead and think about how we can go ahead and combine these. Well, it turns out that what I can do is take the difference of, since both of these functions include the natural logs of my temperature difference, I can essentially add together the heat capacity of my products minus the heat capacity of my reactants to get me my good old friend, the change in heat capacities for reaction. So you may note that this is going to look very similar to our Kirchhoff's law, except for there we had the enthalpy of reaction equal at a new temperature equal the enthalpy of reaction at an old temperature times the change in heat capacity times the change in temperature. And for entropies, it's much more about the natural log of the temperature difference because of that dt over t behavior instead of just the simple dt for enthalpy. So as a consequence, it is worth noting that entropy is going to change with temperature, the temperature of reaction, much less than for enthalpy. Because whereas I have a 10-degree difference in enthalpy, that's actually going to be a fairly large value. The natural log of, say, 308 versus 298 is much, much less. So this value is almost 1. So the only time when we are going to expect our entropies of reaction to show much more of a temperature dependence are going to be under very large temperature differences or under very cold temperatures, where a small temperature difference can make an outsized influence because of this ratio feature. So this brings us to essentially the summary of what we're looking at when looking at entropies of reaction and their potential temperature influences, though again, this is usually a much more minor concern than for enthalpies. So next time, we're going to use what we now know about entropies of reaction to try and look at the favorability of a chemical reaction. Till then, take care.